Gravitational field. You guys probably would have a bit of an idea of what it is already when it comes to gravitational field. Okay, so let's go through this. Okay, now, when you're talking about gravitational field is really a study about gravitational forces, all right? Now, when you have masses tend to exert attractive forces on each other, okay? Meaning to say, if I have one mass m here and another mass m here, because of the nature of gravity, these masses will tend to exert some sort of attractive pull or attractive force on each other. This force is what we know as gravitational force, okay? Usually, gravitational force is significant if at least one of the masses is very large, all right? For example, like a planet like Earth, okay? For our case, like right now, if you're sitting at your table right now, your table has mass, you also have mass. By right, you both are exerting gravitational forces on each other. But then you don't really feel it as being significant because your masses are considered to be relatively small. But if you have a very large mass, let's just say like the Earth, because Earth has a very large mass, the gravitational force that it exerts on the table as well as you will be quite significant, okay, because the mass of the Earth is very large. All right. Now, there is something called gravitational field that you would need to know. Gravitational field is a definition question that will come up quite often. They will ask you to define what is a gravitational field. A gravitational field is just simply a region where a gravitational force is experienced by a mass. All right. So all masses tend to have their own gravitational field. For example, if I have a mass big M here, it tends to have its own gravitational field, such that if I go and place a mass inside the field, this mass will experience a gravitational force, Fg. Fg here stands for gravitational force, okay? So a gravitational field is just simply a region where gravitational force is experienced by a mass, all right? Now, we also have another term called gravitational field strength, all right? Now, gravitational field strength is just something that tells you how strong your field is. A higher gravitational field strength tends to cause a larger gravitational force for a given mass, okay? Now, when you're talking about gravitational field, you can normally represent gravitational field visually by using lines called field lines, all right? But when you draw your gravitational field using field lines, there are a few rules that you need to be aware of, okay? The first one is that field lines must always be perpendicular to your contacting surface, all right? So if I tell you, for example, you have a sphere with circular cross-sectional area and mass, and that sphere has mass m, the field around that sphere would look like this, okay? It will look like this pattern here. Because in the first place, your field lines must be perpendicular to your contacting surface. So the reason why your field lines looks like this right now is because it needs to maintain 90 degrees with your contacting surface. This one is what we call radial field line, okay? It seems to be radiating outwards from a point, all right? Now, another thing that you should also know is that when it comes to field lines, the spacing of the field lines actually tell you the field strength, is a measure of your field strength. The closer your lines are to each other, the stronger the field, and vice versa, all right? Meaning to say, the further apart your field, the further apart your lines, the weaker the field, all right? So if you look at the diagram that I just drew here, if you consider a case where I try to move away from the center, let's just say like this, away from the center, what can you say about the spacing of the field lines? You see, as I go further and further away, the spacing of your field lines is getting larger and larger and larger, right? So here I can say that away from the center, spacing, line spacing increases. Therefore, field strength decreases. Okay, therefore field strength decreases here. The further away I go from the center, because the line spacing is getting larger and larger and larger, the field strength is considered to have decreased. Okay, the converse will also be true lah. If let's say I go towards the center like this, you notice that my line spacing becomes smaller. So this one here towards the center, line spacing decrease. This one I can just say that line spacing decrease. Therefore, field strength increases. Okay, so that is one thing to note here. And then the last thing that you need to be aware of is that field lines normally have a direction. Okay, so when you have direction, you need to draw something like an arrow to indicate the directions. So when you're talking about field lines, gravitational field lines specifically, gravitational field lines always point inwards towards the mass, because the direction of your field line is normally determined by the direction of force acting on the test mass placed in the field. How you determine the direction of your field is determined by the direction of a force acting on a test mass placed in the field. What we mean by that is that, for example, if I place a test mass M here, this mass, the red colored mass, will be attracted to the orange colored mass. This red mass will experience a gravitational force towards the center mass. So the direction of my gravitational force is inwards, right? So the direction of my field line will be inwards. Now, if I'm going to place the mass somewhere else, let's just say maybe diametrically opposite, right over here, the same result can also be seen. This red mass will be attracted towards the center mass. You experience a gravitational force. This is your test mass, okay? So since your direction of your gravitational force is inwards, it follows that the direction of your field must be inwards, okay? Right? So this is how we determine the direction of force on, this is how we determine the direction of your gravitational field, okay? So gravitational field, your lines will always have an arrow pointing inwards, okay? Now, field lines, sometimes they may ask you in your exam to define what are field lines, okay? Field lines can also be known as lines of force. If your question asks you to explain what is meant by field lines or line of force, you can just say that lines of force or field lines indicate the direction of force acting on a mass placed at a point in the field, okay? It's also correct to say it indicates the direction of acceleration acting on a mass placed on the field, because force is what causes acceleration in the first place. Both terms are interchangeable. All right, that is one thing to know. Okay, then next statement, the one below here, they tell you that for spherical mass like a planet, field lines are radial. This one I just explained to you. If you have a spherical mass, your lines tend to be radial because your lines have to maintain 90 degrees with your contacting surface, okay? And then your field strength tends to decrease with distance from the center as line separation increase. This one is what I mentioned. Now, one thing to note is this. There is something called point mass that you will eventually encounter, all right? Now, point mass is just a point where the whole mass is assumed to act. Okay, something like your center of mass that you learn in IGCSE or SPM, the point where the whole mass is assumed to act. So point mass here is just simply a point where the whole mass is assumed to act. So a point has no volume, no size. It's just a point. But for that point itself, you assume your mass is there. Okay. Now, one of the questions that sometimes you will often encounter is this. They will tell you to explain why is it that for the field lines, when it comes to the field lines for a spherical mass, is identical to that of a point mass. Right. So this one is one question that you see quite often later on. One of the questions they will ask you is why is it that the field lines around a spherical mass can be assumed to be identical to that of a point mass? Now, when you're talking about a point mass, how are the field lines around a point mass like? If I tell you a point mass looks like this, the field lines around a point mass generally looks like this. It's also radial in pattern. Okay, it's also radial in pattern like this. Now, when you're talking about a spherical mass has size, has volume. When you try to draw the field lines around it, it will look like this. Also radial because they're trying to maintain 90 degrees with your contacting surface. Now, for your case here, if you try to extrapolate the field lines around a spherical mass all the way into the mass itself, you will notice that it tends to terminate at a point. Okay, it appears to come from the center. Your field lines for a spherical mass tend to come from the center, appear to come from the center. This is your spherical mass. This one is your point mass. Okay. Now for your point mass, you notice that your field lines all appear to come from the center, right? When it comes to a spherical mass, if you try to extrapolate the lines into the mass itself, you will notice that it tends to come from this, it appears to come from the center itself. It's because of this that we normally will be able to say that a spherical mass, the field line is identical to that of a point mass. Okay, that's why we have this statement here. Field lines or uniform spherical mass is identical to that of a point mass. All right, this one we will eventually go through it. Now, then the last statement here, the next statement I told you, the field lines are always perpendicular to the sphere, so the lines come from the center like a point mass. This is what I just explained. Okay, now another thing I should probably mention to you is this. Now, near the surface of the Earth, for small distances, field lines are approximately parallel and equal spacing to each other, thus gravitational field strength is constant. Now, what do I actually mean by that? If you consider, for example, maybe I should erase some stuff. Okay, maybe I'll just erase everything again. If let's say you consider the case where you have Earth like this is say Earth, all right? Your field lines will always be radial. Okay, so it looks like this. Where it's always pointing inwards. Now, let's just consider a case where large distances are considered. Let's just say I consider large distances like this. Hey, wait. For example, I consider large distances. A large distance. When you look at very large distance away from the Earth, you can clearly see that the line spacing is changing, right? So here I can say that for very large distances, field line spacing changes. Therefore, field strength is not constant. Okay. So for very large distances away from the center of the Earth, I can see that the field line spacing is clearly changing. So the field strength is not constant. But some questions later on, eventually you encounter, they will ask you, what if I just consider a very small distance away, a relatively small distance? Say maybe I consider just a short distance like this. This one is relatively small distance now. Okay. This is relatively small distance. What if I just consider relatively small distance? Meaning to say I just look at just this small distance here, the length of the line that I just highlighted. Okay. Now, when it comes to a very small distance near the surface of the Earth, if you were to try and zoom in on the few lines there, what you'll see is that this is, say, the surface of your Earth. The few lines around your surface for that very small distance, this relatively small distance, your few lines will generally look like this. Okay, maybe you need to use a different color. Your few lines would generally look like this. Okay. So when you look at it like that for a very small distance, your few lines, you notice that they are about parallel to each other with almost equal line spacing. So here, we will say that the lines are approximately parallel in equal line spacing. Wait, let me just write this. This one, you can see that the lines are approximately parallel with equal line spacing. Therefore, field strength is constant. Okay, so for very, very small distances considered, we can consider your field strength to be constant because the lines are parallel and about equal line spacing, and they have about equal spacing. All right, so I can say that field lines are, I can say that the field strength is constant. But the moment I go and consider very, very large distances like this, for example, you see, if I happen to extrapolate the line like this, because they were radial in the first place, the larger the distance, the further apart the lines become, you see. So very, very large distance, you can see that if I were to consider this part and this part here, there's a very large difference in the line spacing. Therefore, the field strength cannot be considered to be constant. All right, so that's just one thing to note. Okay, so this is just talking about line spacing or field lines in general, how you look at the gravitational field visually. Now, what if you are interested in finding out the gravitational force acting on a particular mass? Now, for your case here, you want to find out the gravitational force acting on a particular mass. The gravitational force between the masses can actually be summarized by Newton's law. It's not related to Newton's first, second, or third law. It's an entirely new Newton's law. This one is called Newton's law of gravitational attraction, all right, which states that the force of attraction between 2 point masses is directly proportional to the product of their masses and inversely proportional to the square of their separation. So meaning to say, if I have one mass, big M here, and one mass, small m here, if they are separated by a distance of r, the gravitational force between them will be, number one, proportional to the product of the masses. Number two, inversely proportional to the square of the separation. Now, if I wanted to combine these two together, I will end up with this expression where Fg is proportional to mm over r squared. Now, you know that in maths, when you want to get rid of this proportionality sign here, you have to introduce some sort of constant. So the constant that they've introduced here is called your universal gravitational constant G with this value, 6.67 times 10 power minus 11. This value can be found from the datasheet in your exam paper. You don't need to remember this value. It will always be given inside your exam paper. All right. So if you introduce the constant G, capital G here, your gravitational force becomes Fg equals to Gmm over r squared. All right. So this one is the equation that you would use to find the gravitational force for a particular mass. Okay. Now in your AS, you might be thinking in AS, didn't you learn some sort of equation to find gravitational force before? In your AS, your gravitational force is known as your weight, right? So weight is equals to mg, your weight here being your gravitational force. So couldn't you use this equation also to find the force of gravity on a particular mass? This one, yes, you can use, all right? But this one comes with a certain condition. This equation cannot be used for, wait, how do I say this? This equation cannot be used. Okay, maybe I should rewrite this. This equation can only be used if G is known. Okay. Now, your G here is what you learn as free fall acceleration in AS. This one is also known as your gravitational field strength. Okay, this one is known as your gravitational field strength. Okay, this one is actually the next term I will be going through. But now I'm talking about gravitational force, right? So when you're talking about gravitational force, you might be thinking, can I use this also W equals to mg? So the thing I'll just mention is that yes, this equation can only be used if G is known. All right. And then after the next thing I'll just mention to you is that G is not equal to 9.81 or constant. Okay, maybe I don't make things complicated. G is not equals to 9.81 meter per second for very large distances away from the Earth. Okay, because sometimes some people have a tendency to use W equals to mg and G, they always assume it's 9.81 meter per second, carrying forward from your AS understanding. This one I'll just mention to you, when you're dealing with very, very large distances away from Earth, G is not equals to 9.81 meter per second squared. Because as I kind of explained to you already, when it comes to a spherical mass like Earth, where your field lines were radial in the first place, I mentioned to you that for very small distance, G is field strength is constant. Wait, for very small distance, field strength is constant. But then if you consider for very large distance, field strength is not constant. Okay, so for these very small distances here, field strength is constant. If you have a mass of say 3 kg here, wait, sorry, let me just. If you have a mass here, there's 3 kg, and a mass here, there's also 3 kg. This part here, you can actually just say that, since your field strength is constant, G would be equals to 9.81 meter per second squared. You can easily just say that the weight over here, or rather the gravitational force over here, is just mg, it's just 3 times 9.81. Okay, it doesn't matter whether you're here or here, because they're very small distances, relatively small distances, your g is assumed to be constant at 9.81 meter per second. This is what you were doing in your AS last time. In AS, you were moving your masses around, but your masses didn't move very, very large distances. So your G was always assumed to be constant at 9.81 for Earth. But now, when you're talking about this chapter for gravitational field, your masses are not considered to be a very small distance near the Earth. They are very large distances away, going all the way into outer space. So since your distance considered is very large, your field strength at that very large distance away will not be considered as constant. So if let's just say I have that same 3 kg mass, I place it over here, my G cannot be assumed to be 9.81 meter per second squared. This is wrong. It can only be assumed as 9.81 meter per second squared, very near to the surface of the Earth, but very far away cannot, because the field strength is no longer the same. So if I had done Fg equals to 3 times 9.81 here, this one will be wrong entirely, okay, because I cannot use that value of G. All right, so in cases like this, what I'll do is that I'll use this. Fg is equals to Gmm over R squared. If I know the separation between the big mass and the small mass, and I know the value of both masses, I can actually find out the gravitational force between them accurately. Okay, right? So this is just one thing I should mention. Why is it that we don't use W equals to mg anymore? Okay, it's only if you know the value of G at that point. Okay, we cannot assume that G is 9.81 meter per second squared, because at very large distances, it's not constant in the first place. All right. Okay, now, another thing that I should probably mention to you is this. The Newton's law of gravitational attraction is only applicable for point masses, okay? Point mass, just now I explained to you, is just a point where masses is assumed to be, the whole mass is assumed to act, right? So the equation that you're seeing here is only applicable for 2-point masses, all right? But a lot of the questions that you see later on in your past year, they are not point mass. Instead, they are spheres, or instead they are spheres, not point mass. But then we still use the equation Fg equals to Gmm over R squared. Now, the reason why we can still use this equation, even though it's only for point mass, is because when it comes to large objects with size or volume, we normally can approximate them to point masses. We can assume them to be point masses, provided they are either having very large separation or if they are perfectly spherical. Okay, if you have objects whose separation is very, very large, you can actually assume them to be point mass. Okay, example of that is something like this. For example, if you have this mass like this, and then another mass like this is your separation. This one cannot be considered as point mass. You cannot assume them as point mass. But if I have the same mass, but this time the separation is like this, maybe I use a different color. If the separation is like this one, then I can assume as point mass, okay? So the objects that I have can have size or volume then, but provided the separation is extremely large in relation to their size, I can actually assume them to be point masses, okay? So that's why you see later on in your questions, you can actually use this because the separation is considered to be very, very large. If they're very large in terms of separation, we can consider them as point mass. So from there, we can use this equation, all right? And then another thing that would also allow us to assume a large object as a point mass is if they are perfectly spherical. Okay, so just now I think I explained it a little to you already just now in the first page. I told you that the field lines for spherical mass is actually identical to that of a point mass, because if you extrapolate the line for spherical mass, you will see that it tends to come from the center, just like that of a point mass. Okay, so if you see that your object is a sphere, you can also assume it to be a point mass. And then from there, you can actually apply Fg equals to GMM over R squared. All right, so that's one thing to know. Okay, and then another thing here would be that usually the masses that you're considering, the values will be different, all right? But the gravitational force of attraction between them, it will still be equal and opposite to each other as a result of Newton's third law. It could be that maybe this big mass that I have here is 3 times 10 power 24 kg, and then this mass here is maybe just 10 kg. I know that there are going to be gravitational forces exerted between them, but just because this mass has larger mass, it doesn't mean that one of the gravitational forces will be different. Okay, the forces would still be the same for both masses. Meaning to say, if this big mass exerts a gravitational force of say 50 Newton on the small mass m, the small mass m will also exert the same 50 Newton force on the big mass m, okay, due to Newton's third law, which tells you that when two bodies interact, they exert equal opposite forces on each other. Okay, so forces are equal regardless of the differences in the mass. All right, then we move on to the next term, gravitational field strength. Now, gravitational field strength, I explained to you a little just now. It tells you how strong your field is at a particular point. All right, it tells you the strength of your field at that point. A stronger field tends to produce a larger gravitational force for the same mass. All right, so gravitational field strength is denoted with the symbol G. It is actually defined as force acting per unit mass. G is Fg over m. And since just now you learned that gravitational force is Gmm over r squared, you submit into this equation, G is Gmm over r squared divided by m. The small m will cancel off, eventually giving you gravitational field strength as Gm over r squared. When it comes to finding gravitational field strength, you actually have two different equations that you can use. You either use the first one on the left or the second one on the right. Now, which one would you use again depends on what is given to you in your question. All right. Now, if you look at both of the equations, you will notice that there are mass terms on both. But for the left one, the mass is at the bottom. For the right one, the mass is at the top. So one thing to note is just this now. For the first equation, where the mass is at the bottom, this one is usually referring to the test mass. Okay, the bottom mass is the less important mass, is the test mass. But then for the second equation, you see the mass is at the top. That one is actually your more important mass. It's usually the mass that produces the field itself. Okay, so you can just think of it as being something like this now visually. Your test mass, small m, is this one. This is your test mass. Your more important mass is the mass that produces the field. This is the big M. This is the mass producing the field. Okay, right? So these two, just be careful what mass terms are you using, right? If you're using the second one, the mass at the top is the mass producing the field, not the test mass. If you're using the first equation, where the mass is at the bottom, this is the less important mass. It is actually your test mass. Okay, right? So if let's say you're given this current diagram and you want to find the gravitational field strength at this point, if you know the mass that is placed at this point and you know the gravitational force, sorry, okay, let me just, sorry, my pen is acting up. Okay, for your diagram here that you have just now, if I ask you to find out the gravitational field strength at this point, how do I know which one I would use, whether it's the first one or second one? As I mentioned to you just now, it depends on what you're given in your question. So if I want to find the gravitational field strength at this point, if I know what was the mass that I placed here, the test mass that I placed here, and I know the gravitational force that was acting on that test mass, then I will just say G is Fg over m. Okay, if I know the test mass placed here and the gravitational force acting on it, I will just use G equals to Fg over m. All right. But if I do not know the gravitational force on the test mass, but I know the test mass and the mass producing the field, the value of the masses, and I know the separation between them, then I will just use G is Gm over R squared. Oh yeah, sorry. Actually, I don't need to know the test mass. If I don't know the gravitational force and I don't know the value of the test mass, and I don't know the gravitational force, but I know the point at which the test mass is placed, I know the separation, and I know the mass of the main mass, I will just use this. Okay, so it depends on what is given to you in your question. If you know the test mass and the gravitational force on it, you use the first value, use the first equation. You don't know the test mass, you don't know the gravitational force on it, but you know the separation and the mass of the main mass, then you use the second equation. Okay, so that's just one thing to note. Now, field strength is a vector, okay, and it has the unit of Newton per kg. Okay, field strength is a vector, it has an associated direction, and your unit is Newton per kg. You can actually find out why the unit is like that, because gravitational field strength is force over mass, right? So force as unit of Newton, mass as unit of kg, it will be Newton per kg, all right? And because field strength is a vector, eventually you will realize later on, when you want to add up two field strengths together, you need to consider the directions of the fields because they are vectors in the first place. But for this theory chapter, you won't really bother so much about adding them together. That one will be another different chapter. All right, so this one will just leave it first. Okay, now I just need you guys to go to some other part of your notes. This one, you will have to skip it a little. You need to go to page 6. All right, this one is actually tying back with your circular motion question. Sorry, circular motion chapter. Now, in this chapter for gravitational field, you will learn something called satellite orbits. All right. Now, if you have any bodies that orbit a planet, that object or body is a satellite of that planet. You have man-made satellites and you also have natural satellites. For example, the moon is a natural satellite of Earth and Earth is a natural satellite of the sun. Okay. Now let's just consider the case where you have a man-made satellite that's traveling in circular orbit around the Earth. Okay, circular orbit. So this one is your Earth, this one is a satellite. It moves in circular orbit like this, right? Now, since this satellite is moving in a circle, from the previous chapter, you already learned that for something to move in a circle, you must have centripetal force in order for your object to move in a circle in the first place. And centripetal force needs to be provided by some other existing force. For the case of the satellite, your centripetal force actually came from your gravitational force. Because your satellite has small mass m, your Earth has big mass m, you will have gravitational force being exerted on the satellite by the Earth. This gravitational force is actually your centripetal force. It's providing you your centripetal force. So I can say that Fg is equals to Fc. And from here, you can actually use to find some other variables. For example, you can actually use it to find your linear speed v. If you know Fg is Fc, gmm over r squared is mv squared over r. You simplify it, you're going to get v is equals to square root gm over r. Okay. If you want to use it to find some other property, let's just say angular velocity, you can too. You can just say that since Fg is Fc, Fg is gmm over r squared, Fc is mr omega squared. You simplify, you're going to get omega is equals to square root gm over r cubed. Okay, so this one is tying back to what you learned in circular motion. Here you're saying that gravitational force is your centripetal force. Okay, so that part is okay, right? Then there's another part called Kepler's third law. All right. Okay, guys, can you just excuse me for a minute? I need to get something to drink. My throat is hurting. So just give me 1 minute. Let me just get a cup of water. All right. So, okay, right. Sorry for the interruption. Okay, right. So there's the other part here, which is talking about satellite orbit again, but this one relates to something called Kepler's third law. All right. Now, you don't really need to know what's the definition of Kepler's third law. You really just need to know that Kepler's third law relates to this equation, where we tell you t squared to r cubed is equals to 4 pi squared over gm. All right. Now, Kepler's third law applies to any object. It could be a planet, a moon, or satellite that is in orbit around another planet. Let's just say that the objects that are orbiting right now has mass small m, and the object they're orbiting has a mass big M. We know that the centripetal force is provided by the gravitational force. Eventually, if you make use of this relation, you will come to this equation. Derivation is at the bottom here. The derivation is something that you need to know, okay? The derivation in these colored boxes here are required in your syllabus. You need to know how to derive them, okay? That's the only requirement from the syllabus. You need to know how to derive it, okay? That equation that results is known as Kepler's third law. Now, specifically, Kepler's third law tells you this. The square of your orbital period will always be directly proportional to the cube of your orbital radius, okay? So how to come to this conclusion is through this. If you look at this equation for Kepler's third law, t squared over r cubed is 4 pi squared over gm. If I tell you 4 pi squared over gm is constant, t squared is proportional to r cubed, right? Because I can rearrange this as this, right? Sorry, I can rearrange this as t squared equals to 4 pi squared over gm r cubed, right? So if 4 pi squared over gm is constant, t squared is proportional to r cubed. All right. So it's from here that you get this statement, right? The square of the orbital period is directly proportional to the cube of your orbital radius. That's what Kepler's third law is trying to tell you. Now, specifically, one of the things about Kepler's third law is also this. If you rearrange the equation there from here to this one, you will see that this equation can actually be approximated to a straight line equation, where we tell you the y-axis is t squared, the x-axis is r cubed, and then the gradient is actually going to be 4 pi squared over gm. All right. Now, if you were to plot a graph of, say, t squared versus r cubed, like the ones that is being shown right over here, what you're supposed to get is a straight line that passes through the origin. Okay. So this one, you get a straight line that passes through the origin. Okay, so that equation not only tells you that t squared is proportional to r cubed, it also tells you that you can plot a straight line through the origin, provided you plot t squared against r cubed. Okay, now from here, from the graph, it will also tell you one thing. For any given orbit radius, there will only be one specific period of orbit. There cannot be two or more different orbit periods for the same orbital radius. What it means is something like this. If I tell you you have R1, you're supposed to have T1. If you have R2, you're supposed to have T2 only. And then if you have R3, you're only supposed to have T3. So one value of radius will give you one value of period. If you have another different value of radius, you will have another different value of period. Okay, so for one particular radius value, you're only supposed to have one particular period value. Say, for example, this one is 100 kilometer, and then the period is, say, maybe 36 hours. This one is fixed to that radius. It cannot be a case where at 100 kilometer, not only do you have 36 hours, you suddenly have maybe 48 hours, 56 hours, or maybe 12 hours for that period. No, that one doesn't work. Okay, Kepler's third law tells you that one radius will only have one particular period associated with that radius, one value only. Okay, so that one is that. Now, another thing that I should probably mention to you is how you can go and derive the equation out. Now, for the equation, t squared over r cubed equals to 4 pi squared over gm. There are two different ways to derive it. You can use either one, but the way it was derived in the first place is the same. They all come from Fg equals to Fc. So the only difference now is the Fc that you use. Either you're using mv squared over r, or either you're using mr omega squared. On the left hand side, if you use Fg equals to Fc, gmm over r squared equals to mv squared over r, what you need to do is that you want to get rid of v to get period. So v is 2 pi r over t. This one you learn from circular motion. You substitute that one in, eventually you will get t squared over r cubed equals to 4 pi squared over gm. All right. But if you use the other form of centripetal force, which is mr omega squared, you will get gmm over r squared equals to mr omega squared. You get rid of omega to give you an expression for period. So the one equation that you learned from the previous chapter was that omega is equals to 2 pi t, right? 2 pi over t. You sub in for omega. Eventually, you will be able to simplify to get t squared over r cubed equals to 4 pi squared over gm. All right. So these are two different ways of deriving the same equation. Generally speaking, the right one is somewhat easier to derive. It's actually the more common one. Okay, this one is the more common one. The left one is also okay, just that it's less common, all right? But I leave it to you to see which one you want. Okay, right. So the next graph, the next page shows you a graph. This one shows you the orbital period. Sorry, this one they tell you the period versus the cube versus the orbital period, and you're getting a straight line graph. Okay, this one is actually the same equation. T squared over r cubed is equals to 4 pi squared over gm, but this one they change the axis, where this one is r cubed gm over 4 pi squared and t squared. So this one is actually this one, right? They are applying Kepler's third law for all the different planets that orbit around the sun. Okay, so from there they produce this graph out, where they plot a graph of the orbital, where they plot a graph of the orbital radius cube against your orbital period squared. Okay, now this graph, usually when you see this in your question, the thing that will ask you to do is usually to find out the gradient. You see, in your case, this one, your gradient is actually gm over 4 pi squared. You can actually find out the value of big mass M if you know the value of the gradient from the graph. Okay, that's the significance of knowing this. All right. Okay, so rather than me continuing on the concepts, let's just do 1 or 2 questions. Right, the geostationary satellites part, I will go through it once we go through the relevant question. Right, so can you guys just look at your regular worksheet, the one with 62 pages one? Can you guys just have a look at page 1? Okay, just have a look at page 1, right, of your regular worksheet, circular motion and gravitational field. Okay, so this is June 15 P41. Let me just open it up. Okay, so for your case, this one, they ask you to define Newton's law of gravitation. It's actually talking about that Newton's law that we talked about in page 2 of your notes. Okay, so this is a very common definition question asking you to define Newton's law of gravitation. You can just say that the gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. Okay, the important part is only this. The next part, they say, provided that the separation is much larger than the size of the masses, this one is actually not really required. You don't need to write this. You just follow strictly what's inside the notes, you should be fine. So there are 2 marks given here for this definition. Now, the first mark is usually for you mentioning point masses. This is where 1 point always comes from. And then the next point where you say is proportional to the product of the masses and inversely proportional to the square of the separation, this is where the other point comes from. All right. So whenever you define Newton's law of gravitation, please remember to always write point mass. This is the keyword in the law. Point masses only. Okay. Right. So this one you can just slowly copy it from your notes later on. All right. Now let's go through B. Now for B, they tell you planet Neptune has 8 moons or satellites. Each moon orbits Neptune in a circular path or radius r with period t. Assuming that Neptune and each moon behave as point masses, show that r and t are related by this expression gmn equals to 4 pi square r cubed over t squared, where g is the gravitational constant and mn is the mass of Neptune. Okay, now this one usually, when you look at the gravitational field questions and you notice that there's a square term and a cube term, usually you would know that it's relating to Kepler's third law. Okay. All right. Because in your entire chapter, this is the only equation that has a square and a cube term inside. All right. When you see a square and a cube term inside whatever equation that you need to prove, usually it almost always will tie back to Kepler's third law. Okay. And how to derive it. So here they're asking you to kind of derive Kepler's third law in another different form. Okay. So here they basically mention this to you. Wait, let me just get out some stuff. They tell you that this is Neptune. And then they tell you that you have moon that orbits around it in circular orbit. So you can say that the Neptune has mass m n. The moon has mass small m now. Okay, so they're orbiting at a period, they're orbiting at a radius of r with a period of t. So you want to derive out the equation. The first thing normally you can say is this: gravitational force provides the centripetal force that allows your moon to move in a circle in the first place. Okay, now I would suggest that every time you want to write, before you want to write the equation Fg equals to Fc, always write this statement first. When you write out the statement specifically saying that gravitational force provides the centripetal force, because this statement sometimes is where your mark comes from. You have 3 marks here. The first mark actually came from you writing that statement. Okay. Yeah, we know that gravitational force is equals to centripetal force. if you just write this first, without writing this statement, you won't get your full marks, okay? So for some reason, you have to write this statement out before you proceed with your equation, all right? So just remember that. So gravitational force provides your centripetal force. Fg is equals to Fc. So you can just use Fg equals Fc, gmm over r square is equals to mr omega square to derive. The only thing you need to be careful about is that your big M is now mn. Okay? So you try and write it out. You get gmnm over r square equals to mr omega square. And then what you do is that you substitute out omega to become 2 pi over t. All right? Then from there, you just proceed with your derivation. Eventually, you get gmn equals to 4 pi square r cubed over t square. All right? This is the derivation part for Kepler's third law. Okay, so this is all right. Okay, so if this one is fine, the derivation is fine, then you move on to part C. Okay, so let's move on to part C. Now, data for moon Triton that orbits Neptune and moon Oberon that orbits Uranus are given in figure 1.1. So you have two different planets with their respective moons, and then you are given the radius and period for each case. So from here, they tell you, use the expression in B that you just derived to determine the ratio of mass of Neptune to mass of Uranus. Okay, so the case here is that you have Neptune with the moon Triton, and the moon Triton, and then you have another different moon, different planet, Uranus, plus the moon Oberon. Okay, so you have two different pairs of planet and their moons. Okay, now in the case for Triton orbiting around Neptune, and in the case of Oberon orbiting around Uranus, the same equation actually applies to both cases. You can actually say that for both cases, Fg is equals to Fc, which in turn will give you t squared over r cubed equals to 4 pi square over gm. Eventually, like this is Kepler's third law. All right. So what you want to do is that you are trying to find the ratio of the masses, right? You make use of this equation, Kepler's third law, for both cases, because this is the common equation that links both cases together. So something similar to your ratio method that you learn in AS, you try to find out what is the common variable here first. Okay, so in your cases now, your equation derived was actually gm equals to 4 pi square r cubed over t square, all right? But it's still the same form as this, all right? Now, what is common to both cases? The only thing that is common to both cases is the universal gravitational constant G as well as 4 pi square. The big mass M is different for both. The R, the radius of orbit is different for both. The period of orbit is also different for both. Okay, so there are no other constants other than G and 4 pi square. So if G and 4 pi square are constant, you can then say that M is proportional to R cubed over T square. Okay, so from here, you can actually then work out these values here, where you say that Mn to Mu is Rn cubed over Tn squared over R U cube over Tn squared. So eventually you get in this, sorry, Tu, my mistake. Okay, so eventually you're going to get Mn to Mu, Rn to Ru cube, Tu to Tn squared. So those values of radius and period, you already have them from the previous part of your question. Sorry, from the previous page. You know the period, you know the radius. Okay, now you may be thinking right now that this one is in kilometer and then this one is in days. Shouldn't you convert this to meter and shouldn't you convert this to second? Now here you don't need to bother because you see you are taking those values as ratios. You are going to have the units cancelling each other off. So for the radius, it will be kilometer to kilometer. And then for the period, it will be days to days. So the unit actually cancels off. Even if you will change to meter, they still cancel off. Or you were to change to second, it will still cancel off. So there's no need to do any conversion. You can just use the value straight, knowing that the units cancel each other off. Okay, so just take the ratio. Remember to cube for the first set, and then remember to square for the second set. Eventually, you get your answer as 1.18. Just like that. All right. This is one part. Okay, so this is all right. Okay, there's actually a more complicated method where you find out individually the mass of Neptune and mass of Uranus, but that one will be a lot more complicated and a lot more tedious because you have to do your conversions of your units where you convert from kilometer to meter and then days to second. Okay, so this one not really recommended because here you see just now you had gm equals to 4 pi squared r cubed over t squared, right? M can be 4 pi squared r cubed t squared over g. So you apply this individually for Neptune and Uranus, you should be able to get the individual masses, the exact values. And then after that, you have to do the ratio again. So this is actually a bit more tedious. Okay, this one is not something that is recommended. All right. Okay, so next question that we can actually have a look at would probably be page 7. Okay, so let's have a look at page 7. Page 7 will be this one. This one is a diagram, I think. Yeah, the one with the diagram. Okay, have a look at page 7. This is November 15, P43. Okay, now state Newton's law of gravitation. This one is the same question that we just did just now. You can just copy the definition from your notes, all right? The definitions don't change. The marks that are allocated to it are always the same, all right? So gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. This is the only important thing. Provided that the separation is much larger than the size of the masses, this is not important. Don't need to bother. Okay, so that one is all right. Okay, then after that, you look at part B. Part B is somewhat similar again to what you've just done, but this time they're describing a different situation now. Some of the planets in solar system have several moons that have circular orbits about the planet. The planet and each of its moon may be considered to be point masses. Show that the radius x of a moon's orbit is related to the period t of the orbit by this expression. Okay, so again, you see got a square term and a cube term. This one you know should be relating back to your Kepler's third law and how it's derived. So here you can actually say that if you have a planet with mass capital M and its moon with small m that's orbiting around it, your radius is x, your period is t, you would just have to say that gravitational force provides the centripetal force. Now, in your gravitational field question, the moment you see explain your working, this one here, this one almost always relates to this. The explaining your working part is telling you you need to write this. Gravitational force provides your centripetal force. That's where what explain your working here means. Okay, the moment you see the term explain your working, it's actually asking you to write this statement. Gravitational force provides your centripetal force. This is where 1 mark comes from. All right. So the rest of it is just your derivation again, where you say Fg is equals to Fc. So you just say that Gmm over R square is Mr omega square from Fg equals to Fc. The only thing you need to be careful of here is this. Your R is actually your X now. Okay. Your orbital radius is not defined as R in your question. It's defined as X. So you just change the variables accordingly to X. Okay, so it's Gmm over X squared equals to Mx omega square. Substitute for omega, you're going to get 2 pi over T. And then eventually this answer here. Okay, Gm is 4 pi square X cubed over T square. All right, so this is basically the same thing as what we've just done. Okay, the next page will be slightly different than what we've done. Okay, now if you have a look at that, they're telling you right now, planet Neptune has 8 moons, each with circular orbit of radius x and period t. The variation with t squared of x cubed of some of the moons is as shown in figure 1.1. Use figure 1.1 and the expression in B to determine the mass of Neptune. Okay, so you have a planet called Neptune, and there are about 8 moons that orbit around Neptune. So say this one is Neptune now, and you have 8 moons that orbit around it, all at different radius, at different periods. Okay, there are 8 of them. Okay, but all 8 of them are moving in circular orbit around your planet, around Neptune itself. Okay, so since all of them are moving in circular orbit, you know you can say this one, Fg is equals to Fc. Eventually, T squared over R cubed is 4 pi square over Gm. All right. Now here, they want you to find the mass of Neptune. They're actually asking you to find the value of big M here. Okay. But here they give you a graph. So what you want to do is you try to relate that equation to your graph. Basically, you try to relate what you just derived, which is this form, to the graph. So just now we told you that you just now derived that Gm is 4 pi square x cubed over t square. You look at your graph right now, this one is x cubed, this one is t square. You try to rearrange it such that it forms a straight line equation. So this one will be x cubed Gm over 4 pi square x cubed. All right, so this one is y equals to mx plus c, where y-axis is x cubed. Okay, wait, sorry, I think I did this thing wrong. This one is t squared, right? This one is t squared. All right. And then here you will get x-axis as t squared. Your gradient is going to be gm over 4 pi squared. Okay. So to find your m, the mass of Neptune, you just need to find the gradient. Okay. So gradient is gm over 4 pi squared. Right. So all you just need to do is to find the gradient. And then after that, equate it to gm over 4 pi squared. You know the value of g, you know the value of 4 pi squared, so you can actually find out the value of m. Okay, but here you need to be careful a bit because what you're given here, the units are not in meter nor are they in second. You see this one here is in kilometer cube, this one is in day square. So when you do your gradient calculation, you need to be careful to change them to meter cube and second square accordingly. So I can actually say that 1 kilometer cube is 1 kilometer like this in bracket by cube. So this one becomes 10 power 3 meter cube. It becomes 10 power 9 meter cube. And then when you're talking about 1 day square, it's the same as 1 day inside a bracket square. Then this one becomes 24 hours, 60 minutes times 60 seconds square. Okay, so this is your conversion. So here, what you just need to do, pick 2 points from the graph. It could be this point and this point. Find the gradient equated to 4 pi, equated to gm over 4 pi squared. The working is like this. All right. Okay. Gm over 4 pi squared is gradient of the graph. Find the gradient. Remember to do your conversion. And then sub in the values for g and 4 pi squared. Eventually, you'll be able to get the value of big M as 1.01 times 10 power 26 kg. Okay, right, so that is one part. Okay, now, there is also another different method to do this because sometimes some people don't like to find gradient. By default, I always find from gradient. But there's also another different method of doing this, which some people find easier. That one is using single point substitution. What I mean by that is this. Now you see, just now you already found x cubed is gm over 4 pi square equals to us gm over 4 pi square t square, right? So this one you have straight line through origin, right? Now, if it's a straight line to origin, if you see that your equation gives you a straight line through origin, single point substitution to find answer is acceptable. Okay. What I mean by that is that, for example, rather than me using gradient to find the value of m now, what if I just find one value from the graph rather than 2 values on the graph? Say, for example, I try to use this point where I know that this one would have a value of 0.1 and 1.3. Let's just say I use this point where this one was supposed to be my t square. Sorry, maybe I use a different color. Where this one is supposed to be my t square and this one is supposed to be my x cube, right? So what if I just read from one point, get the value for one point, and then substitute it over here, substitute for x cubed, substitute for t square, substitute for m and 4 pi square, sorry, substitute for x cubed, t square, g and 4 pi square, and then eventually find out what's the value of m. If you want to do this by using just one value from a point, it is acceptable, okay? All right, but usually this one is only good if you know the equation gives you a straight line through origin. Okay, if it's the equation that gives you a straight line through origin, you want to find the answer, you can actually just read off from one single point and submit inside. All right, some people find this to be easier because you only need to do one reading and one calculation. Then some people find gradient calculation to be a bit tedious because you need to find two different points. You need to do the calculation a bit more. Okay, so up to you lah. All right, but what I'll just mention is that single point substitution more often than not is only for straight line through origin. If your equation gives you a straight line through origin and you want to find some value out of it, just read one point, that one is okay. All right. Here the question actually mentioned, the marking scale actually mentioned one other thing. This one they mentioned that if you're calculating the answer from a single point solution here, you need to specifically show a line that has been shown extrapolated through the origin. Okay, this is the examiner's comment for this question. If you're trying to find just for a single point the answer, make sure that you show the line is extrapolated to the origin. Okay, because as I mentioned to you just now, single point substitution more often than not is only applicable for straight line through origin only. Okay, so that should be it. All right, so yeah, I think we should just call it a day. Now it's already, I think, 3:40. There are still quite a few questions that we can do. All right, so probably this chapter will take us another 2 lessons to complete. Then after that, we can wrap it up already. All right, so far so good. Right, why is there a 10 power 14 at the bottom when calculating gradient? Oh, it's from here. Net 10 power 14 times kilometer cube. This 10 power 14 is this one. The 10 power 9 is you converting from kilometer cube to meter. And this 10 power 14, right? Yeah. This one was kilometer cube to meter cube. This 10 power 14 is from the graph. There's an additional prefix that power of 10. Okay. Yep. Yeah. So yeah, this is the one. Yeah. All right. The 10 power 14 is your power of 10 from the graph. All right. Okay. So that should be it. Yeah. Gravitational field usually is pretty easy. Just that you need to be a bit careful. I mean, if you do more of the questions, you will notice that it just gets a bit tedious with so many values and so many calculations. You have to change the units, you have to square, you have to cube, and so on and so forth, right? So gravitational field, generally speaking, is quite easy, just that it's tedious. And part of the reason, I think that's also part of the reason why it's always in the first question of your paper, because if it's put in the first as the first question of your paper, generally your mind is still alert and you're still careful, so you're less likely to make errors. All right.